Alright, so today we're going to talk about using some exponents and logs in order to calculate some half-life problems. First thing I want to do is talk about half-life. Half-life is the time it takes for half the sample to decay. So half-life is always some unit of time. And that time could be hours, minutes, years, or seconds. Okay, any unit of time could be a unit of half-life. Okay, some reactions are very rapid, and the half-lives are on the order of picoseconds. Some are very slow, and the half-life could be hundreds of thousands of years. One of the applications of half-life is to radioactive decay, and that's a very common one. But any operation that follows first-order kinetics will have a half-life, and half-life is constant. It doesn't matter how long the sample's been around. So if you've got a radioactive material that's been around for a couple of 100,000 years, the half-life now is the same as the half-life was when that sample was generated. So this is one of the things that makes radioactive waste challenging to deal with, is the long life. Symbol of half-life is generally a T1/2. Okay, so T1/2 might be something like 10 minutes. Okay, that would mean every 10 minutes, 1/2 of the sample decays. So let's say we start with 40 grams. T equals 0. We have 40 grams of material. When T equals 10 minutes, we will have 20 grams remaining. When T equals 20, then we'll only have 10 grams remaining. Okay? And when T equals 30, we'll have 5 grams remaining. So every half-life, every 10 minutes, 1/2 the sample decays, which means how much you started with dictates how much you have remaining after a period of time. Now 10 minutes is a fairly short half-life. Some other applications of half-life besides radioactive decay might be how long it takes a pesticide to degrade in the environment, or how long it takes a pharmaceutical to become ineffective in the bloodstream. Okay, those are other applications of half-lives. Okay, if you look at this, after one half-life, we have the remaining sample is 1/2 of what we started with. After 2 half-lives, 20 minutes, 10 is 1/4 of what we started with. And after 30 minutes, 5 grams is 1/8 of what we started with. Well, we can set this up as an exponential and say that the amount that remains is equal to 1/2 to the n, where n equals how many half-lives have gone by. So 1/2 to the 1 is 1/2. 1/2 to the second, if we have 2 half-lives, 1/4. 1/2 to the third, 1/8. So this gives us a way to make a numerical assessment of half-life and how much material remains. The beauty of this is with a calculator, with a scientific calculator, your exponents don't have to be whole numbers. So if the T equals 15 minutes, then that's 1.5 half-lives. Okay, and so the amount that remains would be 1/2 to the 1.5. So 1/2 to the 1.5 using my calculator, I get 0.3535. Now that doesn't mean 0.3535 grams remains. It means 0.3535 of the original sample remains. So the amount that remains is 14.1 grams. Okay, so there's an example of using the exponent and the number of half-lives. This is a nice friendly example. Okay, for another example, let's scroll down here and take a look at this problem. Iodine 131 has a half-life of 8.02 days. Okay, and iodine 131 is used to treat thyroid cancer, so it has medical applications. Iodine tends to collect in the thyroid, and radioactive iodine will destroy cells, so this is a useful material. So if a hospital was to purchase 25 milligrams of iodine 131, 30 days later, how much would they have left? How much remains? Okay. Well, the first thing we want to do is figure out what N is. And N is the number of half-lives, which would be the total time, 30 days, divided by the half-life. And so N in this example is 3.74. Okay, and remember that the amount remaining is going to be equal to 1/2 to the N times the original quantity, which in this example is 25 milligrams. Okay, so we need to figure out what 1/2 to the 3.74 is, and that turns out to be 0.0748. So the amount remaining is going to be 1/2 to the N times the amount we started with, 25 milligrams, and we're going to have 1.87 milligrams of iodine 131 that's left over after a period of 30 days. Moral of the story, don't stock up on radioactive elements. Buy them when you need them.